Hello and welcome to another Carbon tutorial. In this video, I'm going to explain a technique to speed up your workflow that we call Physics LOD. First, you iterate on a low resolution simulation and get it approved, and then uprez the simulation, maintaining the look but with the physics fully active. Let me show you how to set this up, and then at the end I will show you it in action on a real garment. Here we are with our first example, and I'm going to play the low-res simulation first. As you can see, we have a cloth that's welded to an actor, and I'm animating the welding to create this curtain, shut, and open effect. And we get some nice folding, and let's say this is what we want to achieve. Some broader, bigger folds. And from top down, we like it, and we're happy with it. Now, again, same with the other one. If I now hide the low res and go into a much higher res simulation, let me activate this. What happens when I run this? Well, again, it's gonna take a little bit longer because I have to use more iteration subdivisions, but also we create a lot more folds. So if I was to pause it here, and I'm gonna hide this one and show the other one again, you can see we have a lot less folds here than we have in the high res. So it's a different behavior, but I want to capture the low res with my high res. So let's get started how we can do this. I've set up another simulation using the exact same parameters as the high res, but this time I'm actually passing a goal. How do I get the goal? Well, I'm creating a mesh deformer, which takes the output from our low res mesh and then the start shape as reference, and then deforms the high res geometry to create a goal. And I can show you the goal quickly. Let me hide the simulation, and here we have our goal. And when I run this now, it's gonna simulate the low res first. And then here we can see now the deformed high res based on the low res. And I'm using the skinning deformer. Obviously, if you want smoother results, you use the smoothing deformer, but I'm using the skinning deformer in this example so we can clearly see the low res resolution showing through, and it's just going to make it a little bit more obvious in this tutorial how to tune things. Also, what I want to do is change the lighting setting, and go double-sided. Now we can see it on both sides. All right, so we have our high res matching the low res using a geometric deformer, so the carbon mesh deformer. I'm going to hide the mesh again and show the simulation. So here we have our cloth, and I'm passing in the goal, and now we can tune our parameters. I'm going to reset the strength first to 0, and when we run this, nothing should happen. So no goaling should happen, but we'll see the target. You can see now with these gray lines marked out where our low res wants to go, but our high res obviously is not there yet. So now we need to tune our goal skin parameters. And here's the recommended order of settings. So the first thing you want to do is look at the trail parameters. Your trail stiffness is what you need to tweak to make sure that your cloth follows the goal under large deviations. And the strength is for small deviations. So setting the strength just is for the final snap, so your cloth matches the goal pose. And for anything large, you want to tweak the trail stiffness. The trail viscosity, just like the stretch viscosity and bend viscosity that you can see high up in the parameters, so here and here, is a viscous damping ratio. A value of 2 to 4 is fine, and per default I would always recommend just setting this to 4. So let's do this now and see if we can tune the stiffness. Okay, trail stiffness. We're going to start with a large value, and let's go with a value of 10, for example. I'm going to reset the simulation. Here we go. Reset, and let's run this and see if it matches our target. And we can see very fast that we match it. We don't need to run much further. We see that the structure from the low res mesh, which is coming through in the deformer, is now present here, which means we're very much matching our simulation to our goal, which is not necessarily what we want, at least not to this extent, because we do not want to show these artifacts from the lower resolution. Let's go back and reduce by a factor of 10. Go from 10 to 1 in the trail stiffness. Now we can reset the simulation and run it again. And we can already see we very much still have the underlying structure. Let's go back and again reduce it by a factor of 10. Going down, now we're from 1 to 0.1. And let's reset the simulation and run it again. Okay, This is better, but still not perfect. We get less crunchiness here, still a bit on the bottom, and we're very much still following our goal. Probably too much, so let's try reducing more. What we're looking for is a few lines, gray lines, kind of just like we see up top here, where it doesn't necessarily match the goal. We want to give it a little bit of freedom. And here we still too strict. We still see some of the crunchiness here, the underlying resolution coming through. Go back and reduce it again by another factor of 10. 0.01. And let's reset the simulation and run it again. Now this looks better because we allow more freedom now. You can see there are some more lines here on the edges dragging down lower. We can see some lines here on the edges where it is trailing behind, but a little bit of trailing is alright. And also here we can now see the lines where it's slightly trailing our goal, but still matching the overall shape. So if we reduce by another factor of 10, I expect it to get even weaker, maybe to the extent where it is too weak. So let's add another 0 in it. So 0.001. Reset the simulation and run it. Now we can see more deviations. And we need to decide if this is too much or not. Let's go back somewhere to these frames here and see if this is too much or not. I think we're now deviating maybe a little bit too much. We're losing some of the overall shape. If you can see here, the length of the deviation is quite large here, especially with the fold. The fold is not where it used to be, and I think that's a bit too much deviation. So I think we should stick with 0.01. So the last step was just reducing it too much. So let's go back up to 0.01. The goal skin viscosity injects part of the momentum of the goal pose animation into the cloth pre-dynamic update. What this does is to ensure that we're not trailing too far behind and can keep up with fast motions and avoid overshooting as well. Now, think of the viscosity here as a fraction of the total physics scene frequency. What is the internal solver frequency? Well, it is the scene frequency here in Maya, which is 24 FPS, you can see below, times the substeps. We have subdivisions 10. So we have 10 times 24 is 240 Hertz. That's the internal simulation frequency. So the maximum value you should set the viscosity to is 240. Although we do not recommend injecting 100% of the momentum into the goal pose because this can lead to some artifacts or just some odd behavior. As a rule of thumb, we propose you use 10% of your scene frequency, which here is again 24 FPS times 10 subdivisions is 240. 10% is 24. So you should just generally always set it to 10%, which is 24. If you have slow scenes when it's not much momentum, then you can probably get away with less. If you have very fast-paced scenes, like something flying or moving very fast and your cloth is struggling to keep up with it, you can increase your viscosity. Again, you should not go over 100% of the frequencies. So you should not use more than 240 in this case. Let me reset the simulation and we see where we are. Reset simulation and let's play. And there is not a lot of fast motion, so we would not expect to see too much of a difference in this scene. Okay, still looks good. Now we just want to tune the strength a little bit, again, to help with the last little bit of snapping to our low-res target. The strength, similar to the trailing, we just start high and then go down. So I'm going to start with a value of 10 and just go down in increments of 10 again. All right, reset the simulation. Let's run this. And just like with the trail stiffness being set to high, the strength being set to high, also make sure that you now see your crunchiness coming through from your lower res. And that's why I use the skinning deformer so we can very much see what's happening here. Too much of a strength. We're matching the goalpost too closely, and that's not what we want. So we can see now these artifacts. Let's go back and again reduce it by a factor of 10. So I'm going now down here from 10 to 1. Reset the simulation and press play. And we can already see that we're now not showing these artifacts, so we're not forcing it to very closely match our goalposts, which is nice. We get some deviations here, as you see, the yellow lines slightly deviating, but nothing drastic. Let's have a look from the top and scrub through. We can see some, but the major folds are still preserved, plus most deviations are just on the edges or up top, and obviously we need some smaller folds here because of the welding. This looks quite nice, and I think I'm quite happy with it. So let's say you are in an older version or you don't want to use trailing stiffness. Can you replicate this result without the trailing stiffness? This is what we will look at in the final example here. So let me just take this, deactivate the simulation, hide it, and let's go to a final one. And just like with the one before, we have our goalpost cloth. Same parameters so far, and we're going to tweak the goal skin. So let's just get started with viscosity 24 because we said that's a good value, 10% of the scene frequency, and we don't need more because we have a slow scene. And our strength, let's start where the other one was, with 1. Keep in mind, having trail stiffness set to 0, we will probably need a stronger strength to achieve the same or similar result because now we don't have the trail stiffness helping us. Let's reset the simulation, maybe you want to save and run this scene. Okay, and we can already see that we get quite a lot more deviation from our target. See all of those yellow lines? That means for each point where it wants to be according to the goalpost, but it's obviously not. So let's bring this up. Usually, again, I try to use a factor of 10 faster iteration. So let's go from 1 to 10. 10 was way too strong in the other example. So let's see what we get here. And yes, we can tell all of this crunchiness here, the low resolution showing through. 10 is too strong here as well. So instead of multiplying by 10, let's use a factor of 2. So go from 1 to 2 and reset the simulation and run it. All right, this looks good. We don't see the low resolution coming through, and we see a little bit of deviation here on the sides, but it doesn't seem to be too bad. Let's have a look from the top. Let's just pause it and scrub through it. Yeah, we can tell there is not a crazy amount of deviation here. The points, especially in the bottom and the folds where it matters, actually match it. And just the sides deviate a little bit. So 2 seems to be a good value. If you want, you can try to tweak it a little bit more, maybe see if maybe 3 or 2.5 are better. But I think it's pretty good and we get a pretty similar result. So you might think now, well, actually, why do I need trail stiffness if I can achieve a similar result in this example? Well, I can tell you in the next example, we will have much faster motion and goal skin strength alone will not do the trick. We actually need the trail stiffness. So let's jump right into that example. And that's the example we actually looked at in the beginning. So let's go. Okay, here we are now back to our original scene. And if you remember, we have a cloth over a table and the table spins and we create some kind of nice flowery shaped folds. You can see here. We got these 6 folds here, 1, 2, 3, 4, 5, 6. And then if I swap to the high res again, overlay it, you can see the high res has way more folds and it's not the same shape. So following the same approach as before, I have 2 extra simulations, one where we're going to use trail stiffness and trail viscosity, and one where we just try to do it without the trailing parameters. Let's go to the first one. And you can see it starts pretty well. And just FYI, I started with the same parameters as in the other scene, 1, 24, 0.01, and 4. In the beginning here, everything looks pretty fine. We are definitely not too strong, so we don't show the underlying mesh, and it matches pretty well. But once we start spinning pretty fast, things are gonna get more complicated. Especially here now, we're not matching the shape anymore at all. You can see the yellow lines, they're totally all over the place. They don't match our goalposts. So we need to obviously ramp up the trail stiffness because we're trailing. So let's go up by a factor of 10 and we're here frame 157. So instead of 0.01, let's go up to 0.1 and reset the simulation. Let's go back to 157. It's gonna calculate in the background pretty quickly. I'm gonna see that's probably much better. Now this is already much better. You can see the lines are now much more in line with what we want to go. And just to spare you all of the tuning, I have to go up by another factor of 5 to 0.5. So let me just set this and we can see the final result. Okay, and here we are. And you can see we allow some freedom, but we're definitely matching the shape of all of these folds and we're capturing it pretty well. Even here in all these spinning motions, the main folds remain. We're capturing the overall silhouette. We're not giving away too much. We're not losing a lot of like the size of the silhouette in all the spinning. Same along here. And it's obviously live simulating under the hood now as I'm scrubbing. And yeah, that looks pretty good. It's capturing nicely. And the other test is obviously in the beginning to see if you can see the lower res poke through. And no, this is actually all pretty smooth. So this one is tuned, and we know we can definitely do it with the trail stiffness. So let's go to the last example where we don't use trail. And we just try to tune it with the normal stiffness. I'm going to show this now. And I've already calculated a few frames here. And I've used the existing parameters from the previous scene, which was 2 strength and 24 viscosity. And again, in the beginning, this looks all right, but we already see a little bit more deviation, more lines. And then as I'm scrubbing along, we're going to start losing it, especially here. Look at this. It's way too different. So it's not good. Let's increase the strength. I'm going to go up by a factor of 10, so from 2 to 20. Here we go around frame 130, and we can see the strength is still not strong enough. Let's go to beginning. How we with the low res, well, it's starting to look a little bit crunchy here. You can see some of the textural components come through, but it's not too bad. Well, let's go up instead of 20, which is obviously still not strong enough because we're deviating a lot here. Look at this. Let's go up to 50 to see what this does. And we're gonna look at it from the beginning, because in the beginning is where we need to be wary of, are we gonna go into crunchy material? And we can see this is not looking good now. We're definitely seeing the low-res tessellation poke through this now. So we can't go up to 50, we have to be stuck somewhere by 20. But as we saw, 20 was not strong enough to actually follow it. So now we can't use trail stiffness in this example and not trail viscosity. So what have we got? Viscosity. And as before, we are running at 24 FPS and we have 10 subdivisions. So the maximum we can set the viscosity to is 240. Let's set it to 240, and if this does the job. Reset the simulation and press play to see where we are. So again, we're kind of borderline here by matching the low res, but it's still alright. So far, so good. Looks like we're coping with the motion, but now it's starting to fall apart a little bit. Let's just finish simulating and scrub through and compare. All right, let's see. So we're starting here, that's good, we're following. We're still following, that's all right. We got the overall shape, but here's where we start to now deviate. So we start to deviate quite a bit here in the fold shape. We're losing a lot of the shape up here. Yeah, so really when you have scenes where you are experiencing a lot of fast motion, especially like this angular momentum here, that's when without trailing you cannot keep up. You can see these are just very far behind, so it's not really a proper upscale anymore of your existing simulation. While if you activate the trailing, we're matching it, as you can see here, much closer. We do not have this lack of like extension here. Again, showing the other one. We're lagging behind here. There's quite a gap. The other one here, look at this. With the trailing, we're really matching it much nicer. I hope this explained nicely how you should use the trail stiffness to help cope with goal posing and large deviation, so it really can keep up and doesn't trail behind. Just to explain one more thing again that I mentioned in the beginning. You need to create, obviously, your goal pose. So my goal pose here, I created using the carbon mesh deformer, and I used the skinning deformer. So when you look here, we very much saw this crunchy underlying texture of the low res because I use a skinning deformer. In a real world case, you would use a smoothing deformer, and you just go to smoothing, you go estimated radius and update mapping, and now we get a much smoother result. So the better your goal pose is, actually the smoother your result will be. So we also recommend getting the best goal pose possible before you try tuning the goal pose parameters on the cloth. So your mesh here needs to be as beautiful and as smooth as possible, so your result later on is much easier to achieve a smooth result. And I'm going to show you a quick high-res example of this as well. Here we have an example of a jumpsuit. The jumpsuit runs in a low resolution here on the screen right now, and this is only around 7,000 triangles. And you can see it's got a decent behavior, and we like the overall folds, especially those around the collar and the torso. But now that we've run the low res resolution, we want to try to uprez it. So let's look at the uprez version now. And now we have the high res version. And it preserves all of the major folds up top around the neckline, the torso line, and on the legs, but it adds a lot of believable high-res details to just really upscale believably and make it stand apart from a simple geometric upscale. Because as we all know, if you just use a geometry deformer like a carbon mesh deformer to capture a low resolution for high resolution, you do not A, create the extra details, and B, you do not preserve the collision correctness. While here we run full collision resolution, so the high res will collide but not self-overlap as you get with a lot of the deformers because it's just geometric and not physical. And here's a little close-up. You can see the slider going back and forth revealing the high res versus the low res. And there's a stark difference in resolution, but the overall fold shape is preserved and finer details are being added in the high res to make it a believable high resolution mesh. Thank you for watching, and I hope this approach can help you achieve faster turnaround time and great results. Thank you so much.